All right, so last couple of videos, you guys were working with transformers and that type of stuff. Now, with transformers, transformers are a pretty simple thing. We've had the diagram and stuff that, you get the coils of wire around an iron core, that type of stuff. And of course, transformers, hooked up to whatever they're hooked up to, doesn't matter. The thing about transformers is, good old transformers, these guys need induction in order to work. I mean, that's what they do. They need to use induction, which means you have to have a changing magnetic field, flux, whatever you want to look at, you need something changing. Now, because of that, you can't just turn on a transformer and it runs, because unless the flux is actually changing, they don't operate. And that is why these guys need to actually use AC or alternating current. And this is why we have AC power. And you'll often see on circuit diagrams something that might look like this for transformers, because that's the symbol for an AC or alternating current power supply. You need to use AC in order to create that changing flux. Okay, so that's the point of the top reasons we have alternating current instead of just direct current. You have to have the alternating current in order for transformers to work, so you will have continual induction always possible. Otherwise, they won't do anything. So this is where AC power kicks in, alternating current and that type of stuff. Okay. So if we're in regular classes in my lab, in regular class, we would do this in considerably more detail and show you some more stuff. We'll just do a little general overview for your remote learning, so at least you have an idea where this stuff actually comes from. Now, the transformer type idea and using AC, the two go hand in hand. Without one, you can't, there's no real point in the other. So let's look a little bit at the whole AC type thing. Now, when you have to have the whole AC thing going on, you have to have that changing flux type thing. So let's go back to our original expression we had for induced EMF and that type of stuff. So, for the induced EMF, you guys had negative N change in flux divided by change in T. So we're gonna sort of show you how this actually works, where it actually comes from for AC. If we're gonna look and modify this for induced AC EMF, we're actually going to start with the exact same expression. We're going to start with a negative N change in B over change in T. And we can even expand out that whole flux thing, which would be negative, and then, it's B A cos theta divided by delta T, something like this. Now, the key is, or the trick is, so to speak, with AC generators, and that's what we're talking about, is like AC generators, how they make AC. They don't change. I mean, you got coils of wire spinning in magnetic fields, and they don't change the number of loops or the B or the A. They have things that are spinning. This is what they're manipulating. They're actually trying to manipulate the cos theta. That's the key right there, is to continually have generators spinning in order to produce the EMF. Now, this we're going to do a little side note here. We got to be a little bit careful about something. Suppose we have I'm going to take like a disc. So maybe we've got like a flat disc or something like that, and there we go, something like this. Bring that around. Okay, something like this. There's the center point, and this thing is spinning around and around and around. Okay, put two dots in here. There's an orange dot right there, and I'm going to put a purple dot in there. And obviously they are both, whipping around the circle. Now, between the two, the orange one and the purple one, if I asked you which one is faster, you might want to say the purple one, because it's got a bigger radius, it's got a bigger distance, they go around at the same time, blah, 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 whatever. But it depends on what you mean by faster. The thing about these guys, when these guys go around, when that orange one goes around, it'll go around in a circle, the purple one will go around in a circle. The thing is, after the same amount of time, they will always still be lined up with each other on the same radius. So when you think about how fast they're going, if you talk about basic linear speed, it would be the purple guy. There's no doubt about that. That would be the purple guy. But sometimes linear speed doesn't work well for things going around in circles. Sometimes it's better to use what is called angular speed. Now, angular speed this makes more sense for things that are spinning, and it's a similar idea to linear speed, except instead of the distance you travel, it's the angle you travel. So angular speed is not the change in d over change in t, it's the change in theta over change in t. And if you went back to these guys, they're on the same disk doing the exact same thing. If they both have moved from this line to this line, they'd have the same angular speed because they both went 90 degrees in the same amount of time. Same thing for over here. They'd both have gone 180 degrees in the same amount of time. It makes much more sense to talk about something that's spinning with angular speed a lot of the time rather than regular speed. Now, the angular speed symbol is actually, that looks like a curved in W. It's actually an omega. And you guys might be familiar with omega like this, like ohms and stuff like that. That is the capital. This is lowercase omega. So omega is equal to change in theta over change in t, and that is typically what's used for things that are spinning because it makes more sense. Now, the only thing that sucks, for those of you guys who have taken it, this angle is done in radians. So this is done in radians per second is how you calculate angular speed. And some of you may have not taken radians just yet, but it's a different way of measuring things in terms of angles, that type of stuff. Okay, so this is what we work with. Now, where this comes in handy is if you rearrange this expression for theta, theta would be equal to omega times delta t. I'll put the delta in front of there. And the thing is, this is what we want to use in the expression over here rather than the theta. Because if you put in the angle here, the angle is always changing. It's always changing. This could be anything. But the angular speed is the angular speed. The delta t is the time that you pick. It makes more sense to use this over here than the other stuff. So in the expression, you get negative nba cos omega t divided by delta t, something like that. Okay. Now, the thing is, you got these t's, and you got a t in the top and one in the bottom. They do cancel out because this t is part of a trig function. It doesn't work that way. Now, this is a rate of change of this expression. And again, some of you have taken this, some of you have. Don't worry about it. But this is where good old-fashioned calculus kicks in, and you can take the derivative of that expression in order to make it solvable and usable. And if you don't know how to do this, don't worry about it. I'm just trying to show you how this stuff all connects and where this AC stuff actually comes from. But if you take the derivative for this, you will end up with omega nba sine omega t. And yes, the trig function does change. Okay, so what we can do is we have this expression down here. Now we're going to specialize this a little bit. Okay, omega, that is angular speed. Omega is angular speed. That is the change in theta over change in t. Well, what if I go around one time? And again, some of you haven't taken this yet, but that's okay. If I go around once in radians, if you go around one circle, that is 2 pi radians going all the way around. The time to go around once, that's the period. That's from your wave stuff. That's from your circular motion stuff. That's that. So I can actually switch that out as 2 pi divided by the period. But if you remember, dividing by period is the same as multiplying by frequency. So omega is often found as 2 pi f. So you can actually switch this out for 2 pi f here and 2 pi f here. And that is why one of the top quantities known for anything spinning is the frequency, because now that tells you how fast it's actually going. Okay? Even generators and stuff like that. How many hertz our electricity changes in our AC power, same type of thing. But that's why frequency is such an unbelievably common quantity for anything that's spinning, whether it's generators or engines or anything. Frequency is so common. Okay? Now it's kind of weird. It may seem kind of weird how this all pieces together, but some of you have more math background than others, but that's fine. I just want to give you an idea of where the whole AC thing actually comes from. Okay? Now, if we go to a little simulation here, I can actually show you a little bit of how it sort of actually works as well. Okay, this is the basic diagram of an AC type generator. Got the magnet with magnetic field. I'm not sure why it isn't blue, but whatever. And we've got the coil here, and of course the coil will spin inside, which changes the flux. Now these things here, those are called slip rings because they're rings that slip. And then we have these two grayish type things touching them. Those are called brushes, which are they're non-fixed electrical contacts. They actually move. They can slip across there. So these things can spin and produce electricity. And as it spins, you can see the little voltage needle will go back and forth, and the voltage reading will go back up here. And you'll have bigger flux. You'll have the flux is always changing. That's the biggest thing right there. As the flux is always changing, the induction keeps on happening, and that's basically how an AC generator works. So, like at the the power plant, this would be turned. I'm gonna get a little crank here, but this would be turned by a turbine connected to like water flow or steam flow or something, which then turns the actual coil to actually produce the AC power, and that's generally how it works. Okay, all right. So that's the math a little bit behind it, and that's also a little bit more of the physical stuff that actually kicks in. Now, DC motors are actually a similar type setup, except what they do is they will take out the slip rings and they put in what's called a commutator instead. So instead of the polarity flipping, it'll actually flip the contact to keep the polarities the same, and that's how DC stuff works. And AC and DC, they're really similar to each other, and motors and generators are pretty much the exact same thing, except one is thrown in reverse. So if you spin the thing, it'll produce electricity, it's a generator, but if you put electricity in, it'll cause the spinning, and then it's a motor, and that's basically the difference between the two, okay? Now, the other thing that sort of kicks in is kind of nerdy-ish a little bit, is if you actually go back to that simulation for just a second, you've got this voltage graph right here, which looks an awful lot like a trig function, because, of course, it is based on trig function, and the trig function, of course, is right here. So it's kind of nerdy cool because you've got, when you graph the voltages, it does something like this, which looks just like a trig function. So the other part that's kind of cool is this also looks like a wave, and you've got wave quantities like period and frequency. So you've got trig stuff going on, you've got wave stuff going on, and we also connected this to your circular motion type stuff, which is where we got all this stuff from in the first place. That's because all of these things are webbed together. They're all part of the same chunk of nerdiness. And that's why often when you guys do your trig functions, they're often referred to as circular functions. And they produce wave type graphs, and all these things link together. And the more stuff you take about this stuff, you'll see how all these things actually connect and web together and interrelate and connect to each other. It's cool, it's nerdy cool, but it is still kind of cool. Okay, so that is why we need AC power, so we can use our transformers to have continuous induction all the time. This is a little bit, how the calculation was. If we're in regular classes, again, we weren't remote learning, we'd actually practice with that formula a little bit. That is the AC formula. The AC formula is omega NBA sine omega t, where omega is equal to 2 pi f. That's how you can calculate AC voltage. The great thing is, usually you talk about the maximum voltage. It is AC, so it's always alternating current to alternating voltage. Usually you just end up maximizing it and using maximum voltage, which means this goes to 1 because you've maximized the sine function, so it makes no difference what's inside. And that's often how we typically used it when we practice this a little bit in class to sort of see how it works. But this is the type of stuff that kicks in with transformers, why we have AC power. That's all your plugs are AC, and this is why we need to use it, so we can actually use transformers. And now I've given you an idea of a little bit more of where it actually comes from and how it's actually made.